In this paper, we propose M-ABD, a scalable method for simulating large articulated systems. For a single body, ABD uses a compact affine state with linear kinematics and a constant Jacobian. With co-rotation, the implicit update becomes a time-invariant matrix, so we pre-factorize once. For multi-body systems, we represent each body with control points, making joint constraints simple point relations. We solve this problem in the dual space, a smaller system determined by joint connectivity. This enables topology-aware solvers. Then we recover per-body updates by back substitution. First, we validate single-body dynamics with 3 tests. The T-handle reproduces the intermediate axis instability. The heavy top captures both nutation and precession under gravity. And the physical pendulum better matches the analytical solution than implicit RBD with the same time step. Then we move to articulated systems. Here we evaluate multi-body stability on a long chain with a heavy end mass released from a coiled configuration. The drop creates a strong impulse. With the same time step, Majoko's equality constraints show joint separation, and its articulated model becomes unstable and fails with NANS. Our method stays stable in a single iteration, and it exactly satisfies all joint constraints throughout the motion. Next, we test contact-involved simulation with a ball joint net draping over a cylinder. With the same time step and iteration budget, Mujoko and bullet scatter and PhysX shows joint gaps. Our method remains stable in one iteration. We further scale up this scene. Our method stays stable and the draping remains consistent. Here is a large pulley system. As tension propagates through the pulleys, the chain tightens and lifts a heavy anchor. After release, the anchor drops and the chain slides back, with a brief oscillation from pulley inertia. In this example, we scale the pulley setup to over 1 million links. Our method remains stable and needs only one iteration per step, while enforcing all joint constraints exactly. On a single CPU thread, the simulation takes about 904 milliseconds per step on average. Here we showcase wind-driven tree simulation on a willow model. We first extract a skeletal graph from the input geometry. To model realistic branch compliance, each joint includes a small penalty energy. We then apply a prescribed wind field, accumulate aerodynamic loads as external wrenches, and map them to ABD generalized forces. Next is a pair tree. Using the same skeleton levelized model, compliant joints, and wind loads. With one iteration per step, the simulation remains stable and runs at around 20 milliseconds per step. Shown here is a jointed net drapes over a moving avatar with frictionless contact. With one iteration per step, it stays stable and moves like a flexible garment. Mujoko, bullet, and PhysX fail on this example. In this example, 27 ragdolls collide with a corner pin joint net. The scene has dense impacts, so we use a smaller time step for collision detection. Then we couple a jointed net with a neo-Hookean armadillo. The articulated net integrates smoothly with volumetric elasticity. Dropping and twisting the anchors produces strong shear and torsion, while our solver remains stable. As a stress test, we drop 720 jointed pairs into a bowl. Joint constraints stay exactly satisfied under dense impacts. For embodied AI, we target stable simulation under tight compute budgets. We integrate ABD with IK and motion planning to run Franka-Pick-and-place. Even with one iteration per step, joints and contacts remain stable. Finally, we show a cross-disciplinary example from structural biology. We model the polypeptide backbone as an articulated chain. Each residue is treated as a rigid unit, and most flexibility comes from the 2 rotatable dihedral angles along the backbone. Starting from a 40 nanosecond trajectory of the SARS-CoV-2 spike protein, we keep only temporally sparse observations. We first solve inverse kinematics keyframes to match those sparse markers, and then roll out M-ABD dynamics to fill the gaps in between. The final view highlights the large-scale change by comparing the initial and later frames side by side. Thanks for your attention.